Hello, students. Today we want to talk about infinite limits. It probably sounds like I'm not making any sense when I say infinite limit because a limit is a real number and infinity is not a real number. But it has become commonplace to refer to a function becoming unbounded as x approaches a particular real number by saying positive infinity or negative infinity, and then terming that infinite limit. So even though we're abusing the language a little bit, it is very convenient basically to be able to describe the behavior of the function as we know it's getting unbounded. So give us a little flexibility, give the math community a little bit of flexibility, and understand that this will actually be good terminology when you think about some of the functions that you have already studied preparing for Calculus 1. Now, what I want to do is, before I give you the definitions of a function becoming unbounded, I just want to say something about a couple of examples that you have maybe talked about in your previous courses. So let me share my screen. So up until this point, we have been considering limits that we could compute. And in many cases, we were thinking of the case where we had an indeterminate form. And you might be thinking, what's the difference? So let me just give you an example, a simple example of what we've been doing. So for instance, you could take the limit as x approaches 2 of x minus 2 divided by x squared minus 4. Of course, this is a fairly simple result, but I want to make a point here. So when you look at this particular example and you think direct substitution, then you basically have 0 over 0, which is indeterminate. We use many different algebraic methods to uncover a function with a hole in it. So you've become really good at that. So what would we do? We would do a replacement function. So we'd say the limit as x approaches 2 of x minus 2, and then of course factoring the denominator x minus 2, x plus 2. But then of course the x minus 2 factors absorb. And so we have a replacement identity. That is, we replace the original function with 1 divided by x plus 2. So you've seen that factoring is certainly a way to figure out a replacement function, or multiplying by a convenient one, like a conjugate method, will often give you a function that replaces the original function that has good properties at the particular value of c. In this case, it's 2. And now, of course, this function is defined at 2. So by just direct observation, or again, replacing x with 2, I guess I was looking for direct substitution, we get 1 over 4. So that hasn't changed. So you might be thinking, how is it that we get infinite? What's happening? Well, you have discussed unbounded behavior when you did rational functions, and then also when you talked about certain trig functions. And you thought, okay, well, this is what the graph looks like. We've got division by 0 and the function blows up, so to speak. And intuitively, that worked out very nicely. But we want to say just a little bit more. So if you look at this problem and maybe you consider an alternate value of c. So now what we want to do is look at maybe, if you will, -2. And I'm just going to draw a number line here and put in -2. And what we're going to do is we're going to approach -2 from the left. So we're just going to say left approach. Sometimes it's good just to talk about intuitively what's going on and then add some of the arithmetic that we've been doing to make it more axiomatic and more arithmetic. So in this case, we've got a very different situation. So again, we've got a left limit. So I'm going to say the limit as x approaches -2 from the left. Of course, the minus meaning approach from the left of x minus 2 x squared minus 4. And I'm going to go ahead and factor it just like we did before. I'm repeating myself for a reason. So we have x minus 2, and then we have x minus 2, x plus 2. Now, when you look at this and we do a direct substitution, notice in the numerator, if we replace x with -2, we get a -4. So we can maybe think of this as maybe a function f of x, and think of the denominator as a function g of x, just for convenience. And so we could say that f of -2 equals -4. And now we'll say g of -2, clearly we've got a 0 here in this component, x plus 2, we would say equals 0. So this is a very different situation. Notice we've got a quotient, and many times this is the case in trigonometry when you have ratios of sines and cosines, and so you automatically get these kinds of conditions occurring. So now what we see is the 0 in the denominator is not coupled by the same 0 in the numerator. So you don't get the 0 over 0. So in this case, we say this is not indeterminate. Very different here. This is not indeterminate. And so what we're seeing is that this 0 here, at least by continuity, can be approached from either side. And if we think again of the -2 here, and I've just got the left approach, we can approach -2 from the left, and it would never be the case that the function f would be 0. And so what ensues there, which is not indeterminacy, is a situation where the denominator becomes smaller and smaller and smaller. Now, intuitively, that could make you think, well, the f of x in the numerator is staying well behaved in the sense that it's getting very close to -4. And then the denominator is getting closer to 0, closer to 0, closer to 0. So when you think about fractional arithmetic, and when you divide, say, a constant by smaller and smaller and smaller numbers in the denominator, what you see is that the fraction becomes larger in the case that you have positive numbers in the denominator. And then, of course, if the numbers in the denominator are becoming closer to 0, but through negative values, then you get something that is smaller and smaller and smaller in the negative direction. So going in the negative direction, you're looking at negative infinity, and through the positive values, you're looking at positive infinity. So that's really not a proof, but intuitively, it at least tells you that this is something very different from the 0/0. Now, why is it important that we look at this? Notice, if you can recall, when you talked about inequalities, you would always do a sign test. So if we think we're to the left here of -2, we want to just check out all of these other factors here. For instance, as we approach the x minus 2 here, and you can just think of like a -2.5, we have a negative in the numerator, so we could just put a negative there. And then for the x minus 2, of course, this is also negative. And then, of course, for the x plus 2, again, we're still less than -2, so this quantity would also be negative. So for an overall 3 negatives, we get negative. And so what would happen in this particular case, the function is becoming unbounded, but it's becoming negatively infinite. So what happens is that the sign that is affixed to infinity is arithmetic. It has to be. So this would imply x minus 2 divided by x squared minus 4 approaches negative infinity as x approaches -2 from the left. Now, of course, when you think about sketching graphs, and of course, we're going to do a lot of calculus in this class to get our graphs looking a lot better than this, but we can be intuitive. And so now we know in this particular case, at 2, we have a hole, and we could just put a 1/4 there. I mean, it's a hole, so I can spread this out a little bit. So say we have like this, we'll put a 1 and a 2, and then we'll have a -2 here. And I'm going to draw on an asymptote, and later I'll say a little bit more about this. So this particular problem defines what we call a vertical asymptote. And then, of course, if we look at this particular problem here, again, the x minus 2, this is just what we think of as absorbing. Okay, so if you like, we can put like the 1/4 here, just being not the best scale here, and the 2 here, and just putting a hole there. Okay. Now, again, we'll talk about some things that we've done, and I'll just say here, this is the y-axis, this is the x-axis. This is fairly intuitive, but at this point, what we can think is that the degree of the denominator that you learned in college algebra and pre-cal, again, we'll talk about this when we do limits at infinity, is larger. So we would expect this function to decay to 0 as x approaches infinity. So at least on this side, I can go ahead and sketch this. And then, of course, notice when x is equal to 0, we just get 1/2. So I'll just kind of put the sheet a little and put the 1/2 about right there. So just using a little bit of the intuitive techniques that we learned in college algebra and pre-cal, nothing wrong with them. They certainly got us a long way down the road. And then, of course, likewise here, when we think that, for instance, values here of x less than -2, of course, these values of the function will now be negative. Of course, this just pretty much means that the function is just acting like 1 divided by x plus 2, basically, except when we get to 2 here. So this is kind of a cheat function. And so now we look at this and have our approach like this. So even though I made a big deal about checking all of this. I really didn't need to check these signs because, again, that's just a 1. But I want you to think about just looking at this and thinking, no matter how you evaluate things, the arithmetic will stay the same. Even if you're considering factors that really just go away. The main thing is that because of this 0 that has a preeminence in the denominator away from the zeros in the numerator, that is, we can approach, in this case, the -2 from either side. But we have to be a little bit more careful now, because when it comes to functions becoming unbounded, it's not always going to be the case that the behavior of the unboundedness has the same sign. So just using the techniques from college algebra and pre-cal, you could just look at this, like I said before, as just 1 over x plus 2. And then, of course, at 2, put the open circle at the point 2 1/4. So again, the only difference between this function and the beginning one here is just that right there. But it's a very big difference. So again, when it comes to spotting what we call the vertical asymptote, so let me just spell that out. Vertical asymptote. We say x equals -2. So everything you've learned before in your previous classes, I pretty much did here. Your professor would always give you an example where you had a repeated 0, just to make sure you were being attentive to those in an effort to try to prepare you for the calculus. So we like the repeated zeros, at least between the numerator and denominator, because it doesn't disturb the graph, really. I mean, we've got a hole in it where the function's undefined. So now let's talk about a little bit more about the arithmetic here. So hopefully this is giving you an idea that what you did before is exactly consistent and integrates very well with the calculus you've been learning. Okay, so you actually were doing limits before when you had functions with holes in them. Your professor probably mentioned that, but now it's starting to come together. So now what I wanted to do was just add a few definitions here, and then just do a very simple proof from your homework. So the idea, at least what you're thinking now, is that we only get a vertical asymptote when we have a 0 in the denominator that is not a 0 in the numerator. Again, the fact is that we're also considering that we have enough real numbers, enough interval, that we are approaching from either side. Okay, so we need functions that are relatively nice, but we basically get zeros that are isolated, so to speak, away from the zeros in the numerator. So g of x in the denominator has zeros that are not zeros in the numerator. And like we said before, we can get close enough to the 0 in the denominator without hitting any zeros in the numerator. That's really important. Okay, you always thought about the problems in pre-cal where things were too bunched up. You thought your zeros are too close together, your vertical asymptotes too close together, and it made it a lot harder to draw. And then, of course, you would have to spread out your scale. So that's really what we're talking about. So now, formally, we would say f becomes unbounded as x approaches c from the right or the left. Then the vertical line x equals c is called a vertical asymptote of the graph of f. Okay, that's basically what you learned in your previous classes, but usually the case was your professor would put a function on the board, you would factor the denominator, you'd look for the zeros and just make sure they weren't zeros in the numerator. Okay, so none of that has changed, and that approach was more than appropriate before you take the calculus. Now, arithmetically, what I've done here is I have a right approach here and a left approach here. Like I said before, with most examples with functions becoming unbounded, it's usually the case if you're trying to do a proof that you have to pick a particular left or right approach in order for the arithmetic to make sense. So we don't have often the luxury of looking at both directions. We just isolate to one and focus on that. If you need an example, just consider the last one, okay? So, for instance, what does it mean if we have a function f that becomes infinite? And then you're thinking, I could switch out negative infinity, positive infinity. You see here, none of this is set. You can have any approach you want. The value of the function can become negatively infinite or positively infinite. That's again something that you just have to decide when you're writing something down. Nothing is fixed, and it's probably not the best idea to define this as approach from both sides, because that would be a special case. So now here, this is true. What that mean? What does it mean for something to become infinite? This is the first time we've actually tried to put some arithmetic to this. The standard limit was not too bad. It's not so simple the first time you see it, but here what this means is that if you take any positive number, and we'll just call it m, and the text likes to use m and n's, but any letter will work, of course, there exists a delta. So at least we have the delta from the standard definition, such that if x is within delta of c from the right, notice here we don't have the absolute value because we're simply restricting to values to the right of c. Okay, so we're not looking on to the left of c, so we don't have the absolute value here. That means basically, from an intuitive stance, that if you can get close enough to c from the right within delta, then that would mean that the value of the function would be larger than m. Okay, so the arbitrariness of this is what makes this particular definition useful. It basically means that any positive number, no matter how large, you can always get close enough to c from the right so that the value of the function exceeds m. And so that's a way to talk about infinity. Basically, you're saying that you can make the function value larger than any positive number, and that defines infinity. Remember, infinity is not a number. It simply defines unboundedness. And that's exactly how calculus fits in so well with the infinite, because we can study limits and then we can study the abusive term infinite limit. Now, the other example is just as simple. For instance, let's just consider approach to c from the left like we did with the first example when we approached -2 from the left. So now what you can see is that if we have the limit of f as x approaches c from the left equaling negative infinity, and boy, that's really abusive, equals negative infinity. I mean, you really do have to be flexible in calculus. Again, this is notation that defines the behavior of the function. And hopefully when you did your college algebra and pre-cal, you got used to this. But it's simply identifying the fact that the function becomes unbounded when we say equals infinity, we mean just that. Again, we do have to be a little bit flexible, and I guess it's a good thing we do calculus after you've had plenty of experience with algebra and trigonometry. So this would mean that for any number less than 0, there is a delta such that if x is within delta of c, that is from the left, then you can make f of x smaller than n. So if this would work for any n that's less than 0, then f would approach negative infinity as x approaches c from the left. So I think it's really fairly ingenious the way the author gives you the concept of limit and then the concept of continuity, which is very important because we need to be able to approach these c's without hitting a lot of bumps along the way. We need the function to have some continuity, the g and the f, so that we can do the approach. Okay, so basically the author has built a foundation to the infinite limit in a really skilled way. Now, I want to say something about an example that I found in your homework. And I just want to go through this. It's very simple and done very intuitively. And then we'll work some limits. What I wanted to show you here is to give you a problem similar to the first one we did that had the extra stuff hanging out. But this is how you can look at this arithmetically, and it's actually quite simple. So for instance, if you look at this particular function, you have the limit as x approaches 5 from the left, and I've just written here approach from the left. So now what you can see is as you approach 5 from the left, the values of the function are clearly less than 0. So you're thinking, yeah, that would have to be negative infinity. And again, if you look at this, we have a 0 in the denominator, again, 5. And of course, the numerator is the constant function 1. So it does not have the corresponding 0. So it's not the indeterminate form that we've gotten used to seeing in the previous sections. And therefore, we can at least from the outset look at this and say, yes, that's right. It has to be negative infinity, because if we check the sign of the function close to 5, okay, close to 5, I mean, you don't want to have other zeros of the denominator in the mix. You want to get close enough so that the signs are preserved, so to speak, just like you did when you would do your inequalities. You get too far away from the boundary values, and then the pluses and the minuses are wrong and fall apart. So when you look at this, this is not surprising at all. Indeed, x equal 5 is a vertical asymptote. So that's clearly the case. You can just go ahead and write x equal 5. Remember, a vertical asymptote is a line, and so it needs to be defined this way. X equal 5 is a vertical asymptote. Of the graph of f. Now, if you look at the arithmetic here, it's very simple, and it's just like the standard fare that you do with the regular limits. You work backwards. So that shouldn't be a surprise at all. Now, when you look here, I'm using the same notation as I did before. We'll take an n less than 0. And so we just simply look at what the result should be, because that's what we need to get down here. So we just say, okay, well, we consider the function being actually less than n, where x is less than 5, since we're approaching 5 through values less than 5, okay, from the left. So this is what we want. So again, notice 1 over x minus 5 is negative, and of course, n is negative. So if you want, you can do the reciprocal. Remember, the reciprocal rule works when the arguments on either side of the inequality possess the same sign. Otherwise, it doesn't make sense. So we have this ability to reciprocate each side and reverse the inequality. Now what you can do is say, okay, well, we want to be able to define a delta. So again, we can take the additive inverse of each side, therefore switching the inequality again and getting the additive inverse of x minus 5 is less than negative 1 over n, which now is a positive number. At that point, you can basically say, okay, just like we've done in the past, like setting a delta with the epsilon, we just set delta to be the additive inverse of 1 over n. And now you can see this makes perfect sense, because what's important here is that we consider the fact that if we're going to approach from the left, we need to be at values less than 5. So now when we look at this, we're good to go. So we have 5 minus delta. Again, the negative of delta is less than 0. So we have a number less than 5. Again, if you think about this, let me just draw a little picture. We have our 5. And then, of course, here we have 5 minus delta. And then, of course, we're often used to the 5 plus delta on the other side, but we're not approaching from the right. So this is just part of what we've done before, just half of the symmetric interval. And of course, now we just say, all right, well, let's just suppose that x is less than 5, but bigger than 5 minus delta. Well, if that's the case, we can write this just by definition. And so now we just make a substitution for the additive inverse of delta, which is 1 over n, using this. And then at this point, if you like, go ahead and subtract 5 from both sides. So we're just basically working this backwards. This is the punchline. And then, of course, if you will, go ahead and reciprocate, because again, these have the same signs. I'm just repeating myself. And so we have the function, which is 1 over x minus 5, is indeed less than n. So if you like, just say equivalently, f of x is less than n. And then you might just say, well, n is arbitrary. Because n is arbitrary, we can make f less than any number that's negative by making this assignment for delta. Now, of course, as I've said before, if you take a delta that's smaller than this, it will still work. You can get closer and closer to 5, and there's no problem. So again, the delta is not unique. We often try to look for the largest delta, like you've done in some of your homework, but it's not unique. So just remember, though the arithmetic of the limits definitions is very precise, there is much flexibility. And when it comes to thinking about the limiting process, as I've said before, many mathematicians after Leibniz and Newton refined the arithmetic, because mathematicians were having trouble communicating with each other, because until these things were actually ironed out, precision was not there. I mean, many smart, educated individuals did the calculus, but there wasn't the rigor that we understand today. But that's fine. I think the individuals that are responsible for the frontiers of calculus knew what they were doing and intuitively felt good about their results. And because of their hard work, we are rewarded as we do mathematics and continue to study and look for new ideas, maybe that are yet to be uncovered. Now, what I want to do is say a few things about some very simple examples from your homework. Lots of times, when you look at problems in calculus, you forget about what you learned in college algebra and trig. And what we're seeing now is it's important to be able to at least look at the fact that as we do limits, we've got to say, okay, do we have the continuity? Can we do a direct substitution? We're done. Do we substitute and find indeterminacy, 0 over 0? Later on, we're going to talk about infinity over infinity as we move on. That type of indeterminate form will be generalized more so as we look into calculus 2. And then do we have situations where we have zeros in the denominator, they're not shared in the numerator? Do we have the unboundedness of functions? So we have to be very careful when we do the preliminary work. And so I want to do several examples here. And then I want to talk about a result that I think is very good, that just shares with you some arithmetic properties. Now, let me just say this, and this is very important. Infinite limits are not limits, okay? So you've got rules like product rule, quotient rule, limit of a sum is sum of limits, things like that. I mean, those are no longer valid. Okay, so if you start to write things like that in your analysis, that is not correct. Okay, so what we have to do is simply do the arithmetic, figure in the algebra and figure out what we have, and then we can go back to the problem, check the signs, and then affix infinity or negative infinity. That's all we have at this point. And even if we're using properties of infinite limits, they're still not as sophisticated as the theoretical results we had for standard limits. So please be careful that you don't think of the standard limit results as being applied to infinite limits, since infinite limits are just not limits, okay? So just keep that in mind as you work through this. Now, what I thought was interesting with these kinds of problems is that they highlight some very basic concepts. Now, look at the first one, and notice we have the limit as x approaches 6 from the right and the left of the secant function with an argument of pi x over 4. Now, we had a similar example to this in the continuity section. And a very simple way to think about this function is looking for the asymptotes. Now, when you consider the standard secant function, remember you have x equal negative pi over 2, x equals pi over 2, and then you have x equals 3 pi over 2. So these are the standard asymptotes when you look at kind of the principal period, so to speak. All right. So what you can do is note that the asymptotes are equally spaced. The functions are very predictable, okay, because this is built as the reciprocal of cosine. So a very simple way to do this is to note the disposition and the sign of the pieces here. And so a very simple technique is just to look at the inequality that we get from the first set of asymptotes. Notice here, I've just bounded pi x over 4 between negative pi over 2 and pi over 2. And basically what you see initially is that the pi's absorb, and then you're just left with a very simple inequality. So in order to solve for x, you can multiply negative 1/2 by 4 and get a negative 2. And of course, multiply 1/2 by 4 and get a 2. Now you have a new set of asymptotes, but again, they're going to be equally spaced. So you have a new asymptote, x equal negative 2, and a new asymptote, 2. So you have negative 2, 2. Again, they're spaced by a distance of 4. So you can bump over to the next set of asymptotes just by adding 4 2 to 6, etc., 6 to 10, and then, of course, going in the negative direction, -6 to -2. But now here's the interesting part. Notice here that as you start to shift, this -2 to 2 represents this portion, and then as you move over here to the 2 to 6, this represents the portion that is what? Negative. So this type of analysis can easily give you the signs without having to maybe check a lot of points, just using the basic characteristic of the standard secant function. So now you can think of this approach here. You can just go ahead and put in, let me just go and put in a number line here, 6. And we have the right approach and we have the left approach. And so using the configuration of the original secant function, we have a negative sign for the left approach and a positive sign for the right approach. So for instance, when you have the limit as x approaches 6 of secant of pi x over 4, that will clearly be positive infinity or just infinity. And then, of course, using the arithmetic here in our calculation here, the limit as x approaches 6 from the left of secant of pi x over 4 would be negative infinity. So this is just a simple calculation using the trig functions you learned in pre-cal. That's all you're doing. You're doing a very sophisticated work here in the sense that you are applying your understanding of the secant function and what it means to stretch or compress periods of trigonometric functions. And then by using the characteristics of the original function as to plus and minus values, you can easily calculate the sign of the infinity. For instance, you know that 6 is a vertical asymptote by definition. And then you can affix the sign by using the positive and negative properties of the original, just by extending them as you go through the new sets of vertical asymptotes. Now, what's nice here is that this basically repeats what I did on the very first example. So again, I don't think in general you're going to find the infinite limits to be overly difficult. You just have to think about what you're doing, and I think you'll be good. So notice here I've say state vertical asymptotes. Well, for this particular function here, g of t is t minus 8 divided by t squared plus 64. Well, what I've noted here is that there are no real zeros in the denominator. Of course, you know that there are imaginary zeros, but this is a real analysis class. We certainly want to know when there are imaginary zeros because that's very important. They're not going to impact the graph, and certainly the t squared plus 64 is always positive. I mean, there are really important things to be gleaned from that. But since there are no zeros in the denominator, this function, as you well know from your studies in college algebra and pre-cal, does not become unbounded. And so there are no vertical asymptotes here. Now, this goes right back to the original problem that I did, maybe a little bit repetitive, but an important example. Again, you're asked to state vertical asymptotes. Well, of course, what you did in your previous classes is all now rushing back. You just simply know what the arithmetic means now, which is actually quite important. So if you factor the numerator, you have a t times a t minus 5. And then, of course, the denominator is a difference of two squares. So you have t squared minus 25 times t squared plus 25. And of course, the first factor here is a difference of two squares, which will factor. And of course, this is just like what we had here, no real zeros. You can certainly factor it with imaginary zeros like you're in college algebra, which is fine. And when you take complex variables, this will be very useful to you. Now, notice the t minus 5's absorb. So for instance, here we just say there's a hole at 5. There's clearly no vertical asymptote. But now when we look here, the t having the value of -5 certainly defines a zero in the denominator that is not a zero in the numerator. So if you like, you can think of this as f of t. You can think of this as g of t. And so you see f of -5 does not equal 0, but g of -5 is 0. So again, this defines the vertical asymptote. And of course, by continuity, we can approach the -5 from either side and not run into any zeros in the numerator. And so, of course, t equal -5 would define a vertical asymptote. So very simple, but now you have maybe a little bit better mechanism to do this. But again, just bring back your previous work. It'll pay off rather handsomely. Now, what I wanted to do was just a couple of examples using a little bit more trig, and then make a comment here. I wanted to make sure that this particular example here made sense, because it's a little bit of a departure from some of the problems we've been doing. Now, the very first one is similar to the last one, where you just simply want to analyze what the new asymptotes become. So here it says compute the vertical asymptotes, but it wants you to write them all down. So when you look at this, if we think of the standard period of the tangent function, we have what the principal vertical axis, vertical asymptotes, -π/2 to π/2. So you simply sandwich the pi x between -π/2 and π/2. And let me put in left out my 2 here. Now notice here that the 7, even though it's kind of in the way, obviously has no impact on this, so don't worry about it. So now, of course, the pi's absorb, and you just have -1/2 x and 1/2. So x is sandwiched between these two values, and these become the new asymptotes of the principal period. So now what you can see is you can just extend to all asymptotes. For instance, you see that the distance between the two here is just 1. And so you can just add 1 here. So you have 1/2 to 3/2, then 3/2 to 5/2. 5/2 to 7/2, etc. And then you can go in the negative direction, -3/2 to -1/2, -5/2 to -3/2. So now what you're seeing is that the asymptotes have 2 in the denominator, but you have an odd integer in the numerator. So I think in the problem, they request that you use n for the representation of the integer. And so 2n plus 1 would be fine to represent any odd integer, or we think of the odd integers as not being divisible by 2. Clearly, you know this. And so now we could just have 2n plus 1 divided by 2, which would be more than sufficient, or you could just absorb the 2's and write n plus 1/2, your choice. So again, this is not anything difficult. This is just meant to be a way to show you how you can easily get new asymptotes when the period of the trig function has been changed. Just remember, when we think about secant, cosecant, tangent, and cotangent, the asymptotes are equally distributed throughout the graph. The distance between them is given and is fixed. We don't have, strangeness going on because of the way we actually define these functions. So they're very predictable. Good to have some things that are fairly straightforward. Now, I wanted to talk about some properties here that are actually kind of interesting, and you do have a theorem in your book that addresses this, and they look like this. Before I go through these examples. So there's a little proof of this. You can look through that. It's very straightforward, just using continuity. But it's kind of like the proof that defines the vertical asymptote. But I wanted to just say something here. Say we have and this is done kind of in an abusive way. You can do the plus and the minus if you want, or you can just kind of know that usually the problem will have the plus or minus as opposed to just the C by itself. But a lot of times theorems are written that way, and that's not to be abusive. It just is to keep them very general, because there could be cases where the behavior has the same sign from both sides. So the example or theorem is just written in a very general manner. So let's just say that the value of f becomes infinite, and then of course, plus or minus, that doesn't matter. The value of f becomes infinite as x approaches c, but g actually has a finite value. So I say this is fixed. Now, what's interesting, and this is not at all a surprise, this is what I tell my students: infinity plus finite is infinity. Okay, you think of the infinity as just kind of overtaking anything that's finite, even though it's not, a number. It's just larger than any number. Infinity is larger than any number, and so you can't add anything to infinity, even though it doesn't really make sense to do so. We have to be flexible in our arithmetic to say that it's kind of like, you walk up to an elephant and you touch it with a feather and they don't budge. Of course, it's like the whatever force is absorbed by the elephant, so to speak. So when you do this, plus or minus infinity plus or minus finite, you get infinity. So this is kind of easy to remember. The same goes for products. The only thing you have to remember is that whatever the sign of L is basically determines the sign of the infinity. So it becomes arithmetic, the sign test, which is not surprising because we had to do that in the previous exercises. So just again, think like you're doing inequalities and you're doing the boundary values and you're trying to figure out, when the function is positive. So you're doing a quick sign test, maybe using the zeros of polynomials or trig functions. When you've got a squared zero, you just kind of touch the axis or kiss it. If you have a zero that has an odd multiplicity, you cross. So you have all your tricks to do a quick sign test. That certainly still applies. So of course, in this case, if the L here, this function limit is actually positive, you maintain the positive sign of the infinity. And of course, if this limit is less than zero, the new unboundedness becomes negative infinity. Again, arithmetic. Now, one of the interesting results here that students often have a little bit of trouble with is because usually they can get around it by some algebraic manipulation. And that's fine. I mean, if you rewrite your function so that it looks better and is easier to analyze, there's nothing wrong with that. If you've done it legitimately, you're fine. But here's another case when you think about how we define vertical asymptotes. If the numerator has a value that becomes fixed or starts to settle as x approaches c, but the denominator becomes infinite, then that's where the denominator takes over and the quotient converges to zero, in the sense that the fixed numerator and the denominator becoming larger and larger and larger, then the value of the fraction gets closer and closer and closer to zero. So that, again, is very intuitive. And again, it should agree with the intuition you have about arithmetic that you've cultivated since Algebra 1 or General Math. And if you're interested, I have some more comments about some of these proofs here. They're not hard to do, but I really want you to be able to think about the proof I did initially first, and then if you have more questions, we can say some more about these. Now, one thing I want to talk about now are the examples that I just kind of left to go to that page to apprise you of this. So This first one is very simple. Notice there's not much here. If you think about this, we have the limit as x approaches 0 from the left. So you notice here, I've got the approach, which I've already written down from the left. And we have the g, so to speak, the fixed function, or the function that has limit 7 as x approaches 0. It's constant, so the constant function is its own limit, so to speak. So basically what we have here, notice if we do the sign convention approaching from the left, 8 over x is approaching negative infinity. Again, x equals 0 defines a vertical asymptote, and so that particular unboundedness is negatively infinite. Okay, so now it's like we add 7 to negative infinity, and the 7 is like, again, no impact, so to speak. So the answer is negative infinity. Now, let me just caution you. This is not, you don't say the limit of 7 plus the limit of 8 over x. You can't do that. There is no sum rule here. These are not real limits, so don't do anything like that. Simply use the properties that I just discussed. Now, I wrote over here just a very, maybe a specific example of the elastic property that I talked about. Say we're approaching C from the left, and we're saying that G approaches the number L. And a lot of times, if you want to say something is finite, you just say it's less than infinity, so to speak, that it is a finite number. And then what I've written here is you could have either of these. I just wanted to give you an idea that, you know, the limit of f is C approaches, or x approaches C from the left is infinity, or it could be negative infinity. It doesn't matter. The value here of the quotient as x approaches C from the left will now be 0. So the key is that if the denominator becomes unbounded, even in the positive or negative sense, and the numerator is well behaved and finite, then that quotient will converge to 0. Again, the intuition and the arithmetic are aligned, and it makes sense. So I've got a couple of examples here that I wanted to phrase in terms of this particular property here. Notice in both of these, and I just changed up the approach number here just so we could see something of similarity. So notice we have the limit as x approaches 0 from the left of x plus 7. We can think of that as the g, and then cotangent x as the, in this case, the f. Now notice here, this is interesting. Cotangent is just cosine over sine. And so as x approaches 0, we get undefined. I mean, this is undefined. So when you look at this particular function, you're thinking, oh, wait a minute, that defines a function that's blowing up, because notice cosine of 0 is what? 1, but sine of 0 is 0. So you've got a 0 in the denominator that's not a 0 in the numerator. So now you're thinking you're approaching from the left. So when you look over here, it doesn't matter about the sign, but here's one thing that's interesting about this. I just put 2 of the actual curves of the cotangent function here above their actual periods or intervals that exist between the asymptotes. And so, for instance, what you're noticing here, as x approaches 0 from the left, we would have negative infinity. But as I've written here, it doesn't matter. Basically, as x approaches 0, the limit of the numerator is 7, and the denominator has limit negative infinity. So boom, we're done. This answer is 0. And again, you don't write anything here like, you know, we did before. We're just looking at the fact that these are properties of unbounded functions, of infinite limits. So again, we get a 0. Now, of course, you can do your sine and cosine and flip things around and look at it completely different. But I think it's interesting to note how this works here. We just get these infinity deals with the f. And so notice here, I'll just put a box around this. That's the first case. And in the second case, I just changed the C, so to speak. So now all I did was say x is approaching pi over 2 from the left, and we have x plus 7 in tangent. And now, of course, you can think of, if you will, let me just do the principal period, negative pi over 2 to pi over 2. And we know this has this shape. So as we're approaching, in this case, pi over 2 from the left, the value of the function here has the positive sign, so we affix the positive infinity. But whatever it is, positive or negative infinity, the numerator has the fixed value of 7 in the, well, in this particular case, it wouldn't be 7, it would just be pi over 2 plus 7. It's still finite. Okay, of course, we like the 0 here, we just get 7, but here we have pi over 2 plus 7. So the idea here is we have finite divided by the infinite, so these are both 0. So the main thing about the infinite limit is that it's not the standard limit, so you don't approach it the same way. You do your preliminary analysis to see, okay, what do I have? Do I have direct substitution? I'm done. Do I have indeterminacy? Okay, do I need to look for a replacement function? Okay, that's the key to doing the previous limits. And it takes a lot of practice to get good at the replacement function, but it's worth the time because you find many functions, especially in science and engineering and mathematics, that have holes in them. But one of the most fascinating parts of analysis is the existence of the vertical asymptote, is that the fact that functions that we deal with on a regular basis become unbounded. And trig functions is just in your face unboundedness all over the place with the 4 that are defined in terms of sine and cosine. And then, of course, with rational functions, we have the same thing. And then, of course, at the end of the course, when we talk about exponential and logarithmic, we'll have more of the same. So the interesting thing about the infinite limits is that you have a lot of material from your previous courses that gives you plenty of understanding about them. And so you don't have to spend a great amount of time trying to figure out what you're doing here, just like when you do limits using the algebra that you cultivated in your previous classes. Now, of course, the difficult part is thinking about the epsilons, the deltas, and the n's and the m's. That's the new part, and that takes a little bit more time. But I hope these ideas have helped you to see that there was certainly a reason why you studied what you did in your previous classes. So I hope that this has been interesting, and I also hope that you're starting to feel a little better about the idea of limit. Just remember, we will do limits as we continue through the calculus sequence. You will continue to do limits in your science, engineering classes. So this is a standard operation. It's a standard object of the calculus. And when we define, as I said before, derivatives and Riemann integrals, they are defined in terms of limits. So it's the standard operation in the calculus. Okay, well, we're done. Thank you very much.